This presentation is based on our paper on a multi-degree of freedom extension of the modified bridge system method to decouple vehicle-bridge interaction and is published in the Nonlinear Dynamics Journal. The presentation starts with an introduction on existing approaches to decouple the vehicle-bridge interaction, or in short, VBI problem. Following, it presents the vehicle-bridge configuration adopted in the present analysis. Based on this configuration, the effect of VBI in the response of the system is examined, and accordingly, the bridge is decoupled from the traversing vehicle. Lastly, implications are presented and pertinent conclusions are summarized. The focus of the study is on railway systems, thus the introduction part highlights current decoupling techniques for train bridge systems and their limitations. To accurately estimate the response of a railway bridge, it is necessary to solve for the coupled train bridge system. However, solving for the coupled VBI problem can be challenging in bridge design practice. Therefore, most design standards decouple the VBI problem and solve merely for the bridge system, considering the effects of VBI indirectly via impact factors. The impact factors indicate the relative difference between the dynamic and static response of the bridge, thus merely require a static analysis. Different design standards propose different impact factor formulas to estimate the dynamic effects of vehicles on bridges. In their majority, such formulas are associated with the characteristic length of the bridge. In many cases, though, impact factors do not adequately capture the dynamic effect of vehicles on bridges. Therefore, Eurocode suggested a dynamic analysis based on the moving load method for high speeds. This analysis considers additionally an additional damping ratio and an amplification factor for irregularities to more appropriately take into account the effects of VBI and bridge response. However, this approach still cannot accurately estimate the bridge response compared to the coupled analysis of the vehicle bridge system. Therefore, a consistent decoupling approach is necessary. That requires first adopting more realistic VBI models which allow to identify the coupling mechanisms of vehicles and bridges. Then the characterization and decoupling of VBI should rely on systematic analytical investigations. To this end, the present study decouples the VBI problem based on a simple yet representative of practical train bridge systems configuration. This configuration consists of a multi-degree of freedom vehicle and a multi-degree of freedom bridge. The vehicle is considered as a multi-body assembly consisting of 7 rigid bodies, 1 car body and 2 bogies considered with their vertical and pitching degrees of freedom, and 4 wheels considered solely with their vertical degrees of freedom. Then the vehicle can be divided into the vehicle's upper part, including the car body and the bogies not in contact with the bridge, and the wheels part which is in contact with the bridge. Then the equation of motion of the bridge is formulated by considering the finite element model of the bridge. By gathering the equations of motion of the vehicle and the bridge in a single equation of motion, the gathered coupled equation of motion of the system results. Then the contact model between the two systems considers rigid contact between the vehicle and the bridge, which means that the wheels of the vehicle are in contact with the bridge at all times. By differentiating the kinematic constraint between the vehicle and the bridge twice, the kinematic constraints can be expressed on the acceleration level. The contact force between the two systems results by substituting these kinematic constraints in the gathered equation of motion of the system. The contact force includes now the response of both vehicle and bridge, the effect of irregularities, and the mass participating in the contact between the two systems, indicated here by the inverse G matrix. We can further investigate the different parts of the contact force between the two systems by substituting the vehicle and bridge mass, damping, and stiffness matrices, as well as the vehicle and bridge response vectors. In addition, by substituting the rigid contact kinematic constraints, the wheel's response is eliminated by the expression of the contact force. Thus, additional bridge response and irregularities terms appear. By substituting the expressions of contact force into the equations of motion of the vehicle and the bridge, we come up with a set of equations that fully describe the coupled problem. Note that only the vehicle's upper part equation of motion appears, as the response of the wheels part is eliminated via the kinematic constraints. Having adequately described the VPI problem, we proceed to the identification of the coupling mechanism between the vehicle and the bridge systems, and accordingly of the effect of the traversing vehicle to the supporting bridge. To do so, it is convenient problem in dimensionless terms. The focus is on the bridge systems. Thus, the dimensionless parameters are expressed with respect to the bridge length, first natural frequency, and modal mass. Among these parameters, the stiffness and impedance ratio of the vehicle with respect to the bridge appear. The impedance ratio refers to the ratio of the vehicle's damping to the bridge's mechanical impedance. Also note that both parameters depend on the vehicle's primary suspension system, indicating its decisive role in the coupling between vehicles and bridges. The equations of motion of the vehicle and the bridge can now be written in dimensionless terms. Focusing on the equation of motion of the bridge, we derive some important conclusions regarding the effects of traversing vehicles on the dynamic behavior of the bridge. Specifically, the effect of VBI on the bridge's mechanical system comprises three terms: an additional damping term, dependent mainly on the impedance ratio between the vehicle and the bridge, and including also terms associated with the coupling mass between the two systems. An additional stiffness term, dependent on the impedance and stiffness ratios, and also on the coupling mass G inverse, which causes the appearance of some additional terms. And lastly, an additional loading term. The additional loading term includes the effect of irregularities on bridge response, as well as the response of the traversing vehicles. Last terms are the coupling terms, or in other words, the terms coupling the vehicle and bridge subsystem. We now attempt to decouple the bridge system from the traversing vehicles by eliminating these coupling terms from the additional loading term of the equation of motion of the bridge. To decouple the VBI problem, we apply first an asymptotic expansion analysis based on a small dimensionless parameter epsilon. The small parameter is decided based on the previously dimensional analysis, according to which the primary suspension system of the vehicle appears to play a major role in the coupling between the two systems. Specifically, we first define the frequency of the primary suspension system of the vehicle based on the system of the primary suspension system of the bridge and the vehicle's mass. Following, we derive the damping ratio of the vehicle's primary suspension system. According to these two parameters, the stiffness and impedance ratio can be rewritten as products of the mass ratio between the vehicle and the bridge and the frequency ratio of the primary suspension system of the vehicle with respect to that of the bridge. For practical train bridge systems, the frequency ratio omega obtains values of order 10 to the minus 1. Thus, is considered as the small parameter epsilon to conduct this asymptotic expansion analysis. By substituting the stiffness and impedance ratio, the frequency and mass ratios appear into the equation of motion of the vehicle and the bridge. The asymptotic expansion form of the vehicle and the bridge includes terms up to second order. By substituting the bridge and vehicle response into the equations of motion of the vehicle and bridge respectively, and keeping only terms up to zero order, the zero order response of the vehicle and the bridge can be estimated. The zero order response of the bridge includes external forces acting on the bridge due to the vehicle's self-weight, as well as terms associated to the coupling mass G inverse. The stiffness and impedance ratio do not appear at all. Also, the vehicle's response does not appear into the equation of motion of the bridge, which means that the zero order response of the bridge is uncoupled. On the other hand, the zero order response of the vehicle is zero. Similarly, the first order response of the bridge is estimated by keeping only first order terms. In this case, the vehicle's first order response appears, which however is zero. Thus, it vanishes from the equation of motion of the bridge, which remains uncoupled. Also, in the equation of motion of the bridge, terms related to the impedance ratio now appear. The vehicle's first order response depends on the bridge response and now is non-zero. Lastly, the second order bridge response includes the vehicle's first order response, which is non-zero. Thus, the second order in epsilon the vehicle response. To this end, based on the expression of the uncoupled zero and first order response of the bridge, and neglecting higher order terms with minor influence on the bridge response, we developed an uncoupled formula to estimate the response of railway bridges independently of the response of traversing vehicles. This formula constitutes the extended modified bridge system method. This method accounts for the effect of EBI on the dynamic response of the bridge indirectly via additional damping, stiffness, and loading terms, which are independent of the response of the traversing vehicle. In turn, by substituting the response of the bridge into the equation of motion of the vehicle, the response of the traversing vehicle can also be estimated. The extended modified bridge system method accounts for multiple modes of the vehicle and the bridge, thus it is appropriate for any railway bridge type. Now, to demonstrate the accuracy of the proposed extended modified bridge system method compared with the solution of the fully coupled system, we apply the proposed methodology to a simply supported and a continuous bridge traversed by the same 10-vehicle train. The extended modified bridge system method, shown herein with black dashed line, can perfectly predict both displacement and acceleration of a simply supported bridge compared to the solution of the fully coupled system, which is shown herein with a solid gray line. On the contrary, the modified bridge system method, which is shown herein with an orange line, does not properly estimate the acceleration of the bridge. For the decoupled moving load method, shown herein with a blue line, does not estimate properly neither displacement nor acceleration, as it completely neglects the effect of EBI on the bridge response. The extended modified bridge system method can estimate the response also of more involved bridge models. For a continuous bridge, for example, it can accurately estimate both displacement and acceleration. On the other hand, the modified bridge system method that only accounts for one mode of the bridge is not appropriate for such a bridge that requires a higher number of modes in order to be described adequately. Therefore, the extended modified bridge system method represents a comprehensive approach to effectively decouple any bridge type. I will close this presentation with some major findings of the research presented. The presented research provides analytical multimode expressions of the constituent mechanisms of EBI on the response of the supporting bridge, which comprise an additional damping, an additional stiffness, and an additional loading term. An asymptotic expansion analysis of the response of the coupled system shows that for small frequency of the vehicle's primary suspension system compared with that of the bridge, the vehicle's response does not appear into the zero and first order response of the bridge. This gives rise to the decoupled extended modified bridge system method that solves the bridge system independently of the traversing vehicle. Lastly, numerical applications show that this approach is equally accurate with the solution of the fully coupled system, while outperforms existing decoupling methodologies.